Okay, so this is ECE641, and today we're going to carry on with the chapter about the probability and the estimation. And also, you have the homeworks due, which I sent out emails saying that you can send them in to an email account. There was one, I'm concerned that when I was cleaning up the account, maybe I'm not so good at using Gmail. I don't use it all the time, the Gmail interface. And I think it's possible I could have deleted a homework that got submitted before I requested them, okay? Like before, it was sent earlier. So if you send it earlier before I sent the email asking for the homeworks to send in, send it again, okay? Just to make sure, because I don't recall the name of the person. I just have this, and maybe I didn't, okay, but it's possible. I'll double check if somebody didn't hand it in, okay, but maybe if you handed it in early, resend it, okay? Yeah, and I won't likely be grading them in detail, but I will it's just, if I don't collect them, then it's sort of a milestone. And now some of you emailed me that you were having difficulty with some of the problems. So there's different things we can do. I mean, first of all, maybe you can take multiple passes, okay, through it. And if you didn't get it done yet, that's fine. Keep working on it, okay? Or if you did get it done but decided that you'd like to do a better job, you can just send it in again, okay? So I mean, the function of the homework is for you to learn the material, okay? But in addition, I was sort of toying with the idea of maybe doing some kind of recitation or help session oriented thing. But I want to make sure, maybe I could do that with Zoom. I don't know. I'm just thinking out loud here a little bit, okay? Okay. I can also answer questions in class, but I don't want to take up all the lecture time. So how about this? How about if I try to blast through the material a little bit? You do your best, okay? If you have specific things that you're really hanging you up, like you feel like you're not making any progress, either email me, and if you're not in class here, I can Zoom with you if that's helpful, or I can talk with you. What I've been doing is going right out the doors over here, and they even have some spaces over there where you can have a conversation if you want with a piece of plexiglass between you. But I think some of the conversations maybe can be done more informally or something. They're kind of high-level conversations sometimes. But if you need to, oh shoot, I didn't bring a pencil with me. But if we need to work through something on a piece of paper, we could do that. Okay, I can't really do it in the classroom after class because, well, the other class hasn't been showing up, so maybe that will change, okay? But my point is mainly this: don't panic. It's like The Hitchhiker's Guide to the Galaxy, okay? Have you ever read that book? Because the front thing on The Hitchhiker's Guide is don't panic, okay? So as long as you're willing to work through the material, I'm willing to help you figure out how to do it, okay? I know that for some of you it may seem a little foreign, particularly if you haven't taken 600, but somebody was saying they took 600. And the other thing is that 600 is really more focused on probability. And most of what we do in this class is more estimation, okay? So there's a distinction between those, because probability is really just about modeling mostly. The probabilists mostly just analyze. Probabilists are more like just pure mathematicians. I mean, they're just focused on the structure of the probability as a mathematical formalism. Whereas estimation is more about, we'll talk about it some more, is more about how you estimate parameters from data. It's also can be thought of in a completely formally theoretical framework, but it is different. And 600 mostly focuses on, as far as I know, the traditional focus of 600 is more probability. We actually have a follow-on course, 645, which is an estimation course, but a lot of students also take classes in stat and math. Like there's a class, I think it's 525, which is estimation and statistics. So it is a little different way of thinking about the world, okay? So it takes a little time to get used to it. So don't panic, okay? And now, I think most of you are, even if you're not here, you're synchronous, but there's a few people that are asynchronous, as in they're far enough away. Oh my gosh, this is chalk soup. What the heck? So for those people, we'll also figure something out, okay? Now, commonly used distributions. So, gosh, this chalk is horrible. Okay, forget that. This must be a plot, a secret plot against chalkboards or something. Okay, not that I'm paranoid or anything. There's nothing more fun than a good conspiracy theory once in a while. But anyway, so you have Gaussian distributions. The Gaussian distribution is has the form P of x is equal to 1 over 2 pi. You got to read the notes. Okay, this is one of the things I have to. It's super important that you read the notes, because here's the thing. Like, the flipped classrooms are all the vogue these days. I don't really like it, okay? So I have a concept which I call an unflipped classroom, okay? So this is an unflipped classroom. So the idea of an unflipped classroom is that in the beginning of time, what happened is that people would study things, and then they'd come together to discuss them, okay? And that was called like a lecture. And then somebody got the idea that you should come to lecture and learn the material. Well, that's not really realistic. I mean, I don't know how you guys are, but when I was a student, I would go to lecture, and I became very practiced and at like nodding at the correct times and so forth, so that I would give the illusion of understanding what was going on. And usually I was lost, okay? Because it's really hard in real time, okay, to understand what's going really on, okay? So you can't, that's not a realistic expectation. You've got to read the notes first and work the homework problems, and then be confused, and that's fine, but then we'll discuss it in class, and that will help unravel it for you, okay? But if you come like a completely blank sheet, you're not going to really, it's going to be hard, okay? So time will be much better spent if you actually read the notes. Even if you don't read them, even if it's not perfect, you don't understand everything. But you have the basic ideas in your head, okay? So I call it unflipped because somehow it got flipped where people thought that they were supposed to learn everything in real time during lecture. That's just not, so I'm going to hit the big ideas. It's sort of like, this is sort of like I'm like the music director or the coach or something. So you're really doing the work. You have to learn it yourself. I'm just kind of guiding you through the material, okay? So that's what the function of this is, okay? So you gotta have read it first, because I can't write, these equations will just be endless gibberish that I'll write up on the blackboard doing derivations and things. I want to focus on the big ideas, okay? So this is the Gaussian distribution, which, oh, by the way, I guess I don't, I was going to say I can't remember. I kind of wrote it down from here. Well, I was using the notation here, but I mean, I could have written it down from my head, but the way I usually write it down, because I have a terrible memory, is I know this has to be R inverse. That's the inverse covariance matrix. So X here is a vector. So this is a X then, this is a random variable, okay? The random variable is that squiggly line means it's distributed as normal Gaussian. People sometimes call Gaussian distributions normal, but I don't do that because it doesn't seem like it's very nice to the other random variables, because it implies that they're not normal, okay? So this is some mean mu and covariance R, right? So the idea is that, so the covariants are, so what will end up happening is you can show that the expected value of x transpose, oh, okay, I'm skipping a step. The expected value of x is equal to what? Mu. Just checking that you're there. And then the expected value of x minus mu transpose, oops, I'm sorry, times x minus mu. The default will be vectors are always column vectors is equal to what? R, right? So this is the covariance, this is the mean, this is how it shows up, okay? Now, what also happens is that I'll often write R inverse as B, okay? And this thing is called the precision matrix. Why is it called the precision matrix? Because if you have a one-dimensional Gaussian random variable, then R is the standard deviation. I'm sorry, it's the variance, okay? So as the variance increases, the, okay, as the variance increases, okay, well maybe I should just, for those who may not deal with random variables a lot. So the idea is this is the mean, and that's the distribution, and this thing here, that's the standard deviation, and then the square of the standard deviation is the, okay, oh, well, okay, maybe it's two, you know what I mean here, right? So this is going to be mu plus sigma, and this will be like mu sigma. It's a measure of the width, okay? And the square of that is then the variance, okay? So as the variance increases, the thing becomes less well defined in terms of its position, right? So as the variance decreases, the thing becomes more well defined in terms of its position, right? So if this was a measurement, as the variance goes down, as the standard deviation goes down, the precision of the measurement goes up, okay? So that's why they call this the precision matrix, because it's the inverse of the covariance. So as the covariance increases in size in some sense, it's not a scalar in the general case, then the precision goes up. I mean, yeah, no, I'm sorry, yes. So if the standard deviation, if the covariance increases, the precision goes down, okay? Because it's 1 over it, okay? Okay, and then this is always here because it's a normalizing factor that makes things work. Okay, and so this thing is like, what happens is that as the variance gets bigger, the volume under the thing grows, right? So in the one-dimensional case, this has to be, so okay, as R gets bigger, you got to divide by a bigger number to keep the total area the same, because this has to integrate to 1 because it's a probability density. So, so clearly it has to be 1 over R. This is the determinant of R. So why do you take 1/2? Well, in the special case of the scalar case, R would be the variance, right? So if you increase this way, if you want to keep the area constant, you have to divide by, if it gets wider, you have to divide by a larger number, proportional to the width, right? Because the width times the height is the area. So you're going to have to take the square root here, because otherwise you'd be dividing by the variance. You really want to divide by the standard deviation. So that's how you remember this. And then this, well, you got to just kind of memorize that, except P here is the dimension of X. So in the case where they're independent, the components are independent, then you'd multiply together the things. So you'd have one term of this would be the square root of 2 pi for each component of the dimension. You'd multiply them together p times, so you raise it to the power p, okay? So I can just work this out every time I need to You'd be thinking, well, how could it possibly be after 50 years you're still working this thing out every time, or whatever, 40 years. I don't want to make myself too old. But yes, it's true, because I can't remember it, so I just figure it out every time, okay? But it's good for you to think through it, okay? So that's the probability distribution. And then what happens is that R is equal to, okay, R is equal to R transpose, okay? So this thing here must be, R must be symmetric. Are there two M's or one M in symmetric? Is that two M's? Is that correct? Okay. Symmetric and positive definite. So what do I mean by positive? Actually, yes, it's positive definite. That means that by positive definite, so this is symmetric. Positive definite means that for all x not equal to 0, x transpose Rx is greater than 0, okay? It's positive definite because it's strictly greater. So I make it positive definite because if I allow it to be positive semi-definite, in which case it could be 0, you get messed up distribution. I mean, it won't be a legitimate probability density function, because essentially what will happen is that you could have a standard deviation of 0, okay? And that, so you got to choose your poisons, and this is the poison I chose. This leads to problems because it's kind of an open set for the parameter space, but okay, we'll talk about that later. Okay, so this is true. Now, if something is a symmetric matrix, it turns out that the eigenvalues of and eigenvectors of a symmetric matrix are real, and the eigenvectors are orthonormal. So honestly, in my opinion, I don't really like eigenvectors for non-symmetric matrices. I mean, sometimes you have to use them, but they're kind of weird. Singular values usually make more sense physically. But for symmetric matrices, which is usually when you're talking about eigenvalues, but not always, the physical interpretation of the eigenvalues is really makes so much sense. It's kind of beautiful, okay? And which is that you have E lambda E transpose. If you've taken another course with me, I've talked about this before. So E here is the set of eigenvalues. So it's eigenvectors E1 through EP. Maybe I should have started 0, but I started at 1. Okay, so those things are orthogonal and normal, the eigenvectors, okay? They're orthogonal by convention. Okay, I'm sorry, they're normal by convention, and they're orthogonal, you can prove it because the R is symmetric. So they're normal by convention because you can just always normalize them. Okay, so you just take their, when I say they're normal, I mean that the L2 norm is equal to 1, right? If they're not normal, you just normalize them. So you just scale them by whatever scalar factor you need to make them normal, okay? And orthogonal means that EK inner product, inner product EJ is equal to delta K minus J, where that's a delta function. It's equal to 1 when K and J are equal. Or it's equal to 1 for when its argument's 0, and it's equal to 0 otherwise. So the idea is that if K and J are not the same index, then the vectors are orthogonal, okay? So a simple way of representing that is that E transpose E equals I. If you think about it, E transpose E equals I is exactly the same equation. Because when you take the transpose of E, you'll just take the transpose of each of these elements. How many people in here are comfortable with linear algebra like this? Is this lasting? Okay. If you haven't had a lot of linear, if there's people out in the studio audience who aren't comfortable, you just have to work through it a little bit and make sure it's clear in your mind. But it's pretty nice stuff. Okay. So that's so this is the orthonormality condition, okay? And lambda here, so this thing, lambda, is equal to a diagonal matrix, and it's equal to lambda 1 through lambda p, okay? So it's the eigenvalues, okay? Those are the eigenvalues. To see that that's true, what does it mean for something to be an eigenvector? You take R, you multiply it by EK, and you should get lambda k times EK. That's what it means to be an eigenvector, right? But that works out because you get E lambda E transpose times EK, right? Well, so this is equal to that, right? Now, if you look at E transpose, that's equal to E lambda, and this is E1 transpose through EP transpose, right, times EK. Well, what's going to happen is that when you multiply by this, it's going to go down. The inner product with all the other vectors is 0, except for the one that's the same, okay? So you're just going to get a 1 in the position associated with, you'll get like all zeros, but you'll get a 1. You'll get a 1 in the position, in the kth position, okay? And when you multiply that by this diagonal matrix here, lambda, well, then you'll just get, E times, what'll happen is that you'll get lambda k times zeros with a 1 in the kth position. So when you multiply that by this, you'll just get EK times lambda k, which is exactly what you said, okay? Now, so what happens then is that for the multivariate Gaussian distribution, okay, I don't have time to go through all this in detail, so I'll just tell you the answer, but you have to figure it out. It's not that complicated, okay? Which is that what will end up happening is that E looks like a rigid is that how you spell rigid? Rotation. That's a little bit of a lie because it actually can also have some it can also involve a reflection like you would have in a mirror. But let's ignore that because it doesn't, it's close enough, okay? Actually, it won't really matter for this application. So, so what happens is that, so what this means is that the distribution of x, if you did like a scatter plot, and this is x1 and this is x2, you'll get something like this. You'll get a distribution that looks like this. This axis will be like E1. Oh, this will be E1, and this will be E2. That'll be the directions. The eigenvectors give you the directions of the principal axes of the ellipse that you would get from a scatter plot of the multivariate Gaussian distribution. Oh, this all assumes that the expected value of x equals 0, okay? Because so that it makes it easier to do the plot. So you get something like this, and then what happens is that this distance here is lambda 1 square root. Because lambda 1, the eigenvalues of this matrix are like the variances of the multidimensional distribution. So if you take the square root of the variance, you get the standard deviation. So this is like the standard deviation, and this will be lambda 2. So the interpretation is that these eigenvalues, the lambdas here, these are like the standard deviations of the ellipse. And the e's are the orientations of the ellipse. And a multivariate Gaussian distribution always looks like a multidimensional ellipse, okay? It always has that form. The special case would be when all the eigenvalues are the same. If all the eigenvalues are 1, then what will the shape of this ellipse be? It'll be a circle, right? And if it's a circle, then a circle's rotationally invariant, right? So it doesn't matter what E is. So if R, in the special case where R is EI, because it's where the eigenvalues are all the same, then this is the identity matrix. Because identity matrix is a matrix that's diagonal with 1s on the diagonal, right? And this is times E transpose. That's just E times E transpose, but E times D transpose is I. And the I is the covariance associated with what? What if the covariance of a Gaussian multivariate Gaussian random variable is I? What does that tell you about this distribution? Let's take a little time and think about this, because I blew through a lot of things and you got really good at looking at me and nodding. Actually, even with the masks on, it's pretty good. I gotta give you a lot of, you have that note. Okay, but now you're like, what the hell is he talking about? It's not that complicated, guys. Okay, so N0R, okay? So this is a multivariate Gaussian distribution. X is a vector, right? It's a column vector. It's random. Each of its components is a Gaussian random variable, okay? Right? Now, if R equals I, what does that tell you? In that case, the covariance is like this. It's 1s and then 0s everywhere else, right? What does that tell you? And let's say that, by the way, mu is equal to 0, okay? That means the components are uncorrelated. Now, okay, if the components are uncorrelated and it's a Gaussian random vector, I'm skipping things. It's all in the notes. You got to read it, okay? Because I can't go through it all, okay? I'm just hitting the big ideas, okay? If you got, if the components of a Gaussian random vector are uncorrelated, what do you know? Excuse me? They got to be independent. Are uncorrelated random variables always independent? No. But for Gaussian random variable, uncorrelated random variables are always independent, okay? So what does this tell you about the components of this Gaussian random variable, of this vector? They're independent. What's their mean? 0. What's their variance? 1. Their standard deviation is what? 1, right. Now if I have, if R is equal to, say, lambda like this, okay? So it's equal to, say, lambda 1 through lambda p, right? What does that tell you? The components of the Gaussian random vector are independent with variance lambda, right? So so if I have a computer program, I want to generate a random, multivariate Gaussian random vector with this distribution. What do? You just generate a bunch of independent Gaussian random variables, right? And excuse me? Yeah. That was good. I heard somebody saying something that sounded like what I was hoping for. Oh, you don't multiply them together. They're just, because they're each, you just populate the vector with them, okay? But then what do you multiply? You do want to, so let's say you have a Gaussian random generator, but let's say it only generates Gaussian random variables with standard deviation of 1, which is the same thing as variance of 1. but I don't want it to have a standard deviation of 1. What do I want the standard deviation to be?
Each component by the square.
Yeah. Yes. So you generate a normal Gaussian random variable with mean 0 and variance 1, right? So we'll call that u, right? And then xk, the kth component, is equal to lambda k is going to be equal to, you take the square root of lambda k times u. I'll make this k. So that's what you actually do when you write the code, okay? That's how you generate Gaussian random variables. That's how you would generate a multivariate Gaussian random vector with this distribution. If you have a more complicated distribution, I'll let you look at it in the notes, but to prove it. But what you would have to do is this. You first generate u, which is normal with mean 0 and variance I, okay? Then what you do is, so you take u, you multiply it by, so you sort of do pointwise multiplication by, okay, actually, you multiply it here by this to the minus 1/2, okay? Oh, to the 1/2, I'm sorry, to the 1/2. You see, you take the square root of this. So what will end up happening, each component you multiply by the square root of the corresponding lambda. And then you multiply by e. I think that's right. I'm pretty sure that's right. And then that gives you the Gaussian random vector f. So this is a strategy for generating a multivariate Gaussian random vector with any distribution. To do it, you have to take its, so this is R0, I'm sorry, it's N0R. So if somebody gives you a covariance matrix R, you can generate a Gaussian random vector with that covariance, but you do have to get its eigendecomposition. I'm pretty sure you multiply by E, but it might be you multiply by E transpose. Yeah, I'm pretty sure you multiply by E. But you can double check that, okay? Now, so you can read all these notes, blah-de-blah-de-blah. If you have a bunch of Gaussian random vectors, okay, this is called a jointly Gaussian random vector, technically speaking, okay? And the reason it is, it's not, I just want to point out that there are some perverse things that one can do, but generally don't happen in real problems, but sometimes do, okay? One is that pairwise independence this does not imply joint independence, okay? And there's a problem in the homework on that. A good example of that is if you have, I've given this example before, but if you have coins you flip. So let's say instead of the coin being head or tails, the coin is either plus or minus 1 because it's easier to do the math, okay? So tails is like minus 1 and heads is plus 1. So if you flip 2 coins, they're independent. Then you synthesize your third coin flip by just multiplying them together. Well, if you think about it long enough, you realize that any 2 of those random variables, there's 3 random variables. The first coin flip, that was physically, you flip the coin. The second, you flip the coin. The third, you didn't really flip the coin. You just multiplied these 2 together and you made up the coin flip, okay? But those 3 random variables, any pair of those 2 pair of random variables are independent. But clearly, they're not jointly independent because if you know 2 of them, you know the third. So joint independence does not imply, pairwise independence does not imply joint independence. Pair individual Gaussian does not imply joint Gaussian. Okay? So if you have a bunch of random variables, they're each individually Gaussian. It doesn't necessarily mean they're jointly Gaussian. The distribution I gave you was sort of my starting point for the definition of Gaussian random vectors. And if it follows that distribution, it's always Gaussian. But it could be that each individual scalar random variable follows the Gaussian distribution, but that they don't jointly follow the Gaussian distribution. So what happens is there's something wrong. The way to think about that is that you have like, okay, I'm afraid to draw it because I'll probably get it all messed up, but that this is like x1 and this is x2. So you have a random variable which has two components, okay? And if you think about it, the marginal distribution, you probably know this already because I'm assuming you've had some probability. It's just that we're talking about it in some more general terms. But if you have the marginal distribution of one of the random variables, say x1, is like what you get if you integrate the two-dimensional random variable. So it's like you get some function like this, and you get some So you get two Gaussian random variables, say both with mean 0 and variance 1. So just because these two projections, this is called a projection, just because these two projections of the two-dimensional function are Gaussian doesn't mean that the function itself is Gaussian. If you think about it, if you discretize this, there's way more degrees of freedom in the two-dimensional thing, okay? So I'd like to come up with some kind of crazy counterexample right now, but maybe you could do some kind of crazy thing where you had like a Gaussian random variable like this, and then this was all 0, and that was all 0, and then you had a Gaussian random variable like that. So you took this projection, it looked like a Gaussian random variable, and took this, it looked like a Gaussian random variable, but the two-dimensional thing looks crazy. It's definitely not Gaussian, okay? I just wanted to point that out. Okay, Bernoulli random variables. They're going to be important, but maybe I'll let you read them out. Oh, sufficient statistic. Okay, so what happens is that now we're kind of getting into estimation. There's a very, very, very important concept of a sufficient statistic. So first of all, what is a statistic? So x is a random quantity. It has some distribution. Okay, and I'm going to write this, okay? It's a little bit, people use different kinds of notation. So this thing is a parameter. It's not random. Honestly, better notation is to write it like this. Oh, excuse me. Oh, I'm sorry. That was not like a diseased cough, okay? Believe me, that was just a chalk dust cough. So this thing here is it's like a vector of numbers or something, but it's not random, okay? It just parameterizes a family of distributions, okay? So it's some unknown parameter. So for example, in the Gaussian case, theta was mu and r, okay? But for other distributions, there will be other things, okay? Now, then this is a random quantity. It might be a vector. Usually it's a vector, actually. And, but I'll write it like this only because it's a little cleaner notation, okay? But it's a little deceptive because it sort of implies that theta is a random variable, but it's not, okay? Now, then what happens is that I can have something like a t of x. Okay, t of x is a statistic. Okay. Oh, I'm sorry. T of t of x. T of x is a statistic. Any function of x of the random variable is called a statistic, okay? And a statistic is said to be sufficient if it has the following property, that p of x given theta is equal to h of x times g of t of x given n theta. Sufficient statistic. Okay, well, what is a sufficient statistic? A statistic is sufficient. Well, first of all, let me point out something, that the identity function, so one possibility is that t of x is just x. So it doesn't do anything. It just takes the whole thing, okay? So the sufficient statistic, in that case, the identity function is definitely the sufficient statistic. X is a sufficient statistic because clearly you can express p of x given theta in this form because, yeah, okay, it's even hard to explain. It's so obvious. Okay, maybe it's not obvious. Okay, here's the idea of a sufficient statistic. It contains all the information you could ever reasonably need in order to estimate the parameter theta. So any additional information is useless. And the reason that is true is because if you can express the probability distribution in terms of what it's saying here is that the only dependence on theta is through a function which only depends on t. So therefore, this thing's just a normalizing constant. It doesn't really matter. So you can estimate the parameter theta from just knowing t. So an example of sufficient statistic is if you're estimating the mean of a Gaussian distribution, we all know, okay, so if you have x is distributed as a normal with mean mu and variance r, okay, then sufficient statistic is what? Okay, we all kind of know this. Oh, let me write it over here. Oh, I need a little more space. Okay, actually, I could make this thing go up. It's getting in my way. Example. Okay, so what we have is we have xn is distributed as normal with mean mu and variance r, okay, for n equals, say, 1 to n. I want to make sure my notation's correct. Oh, okay. We'll use a k here. Okay. So, and these things are independent and identically distributed. And to show that you're part of the club, the way you write this is as I, D, okay? And I don't know why, but you use lowercase just to, you know, it's sort of like knowing the secret password, okay? So, so you say IID. This is a very common assumption in statistics. You assume that you perform an experiment. Each time you perform an experiment, it's independent. So the samples you get are from some distribution, which is parameterized by some theta. In this case, theta is mu and r for multivariate Gaussian distribution. But each experiment you perform is independent. So you say the samples are IID, with this distribution, okay? And now your goal is to estimate the unknown mu and r, okay? So it turns out that sufficient statistics for this problem are what, okay? Sufficient statistics are B is equal to the sum from k equals 1 to n of xk. So you sum them all up. If you divide that sum by n, you get the mean. Guess what? We're going to find out the mean's a pretty good estimator for mu, okay? Okay. And then S here is equal to the sum from k equals 1 to n of xk times xk transpose. So together, B and S are sufficient statistics, SS, for mu r, the mean and covariance. And you can guess, maybe, that you can use B and S to estimate those. But the important thing is that you don't have to keep all the x's. Let's say you had 1 billion observations of this. Let's say that each of these vectors had dimension 20, okay? But you had 1 billion observations. That's a lot of data. You can get rid of most of that data by just taking a running sum of the sum of the actual vectors as a sum of, this is sort of an outer product of the vectors. And this is all the information you need in order to estimate those parameters. You don't need, you can throw away the other stuff. It's extra junk you don't need, okay? So it's called a sufficient statistic. One other thing I just want to say before you leave is that, remember, mu and r, they are not random. So these are numbers. Are B and S random? B and S are random. Why? Because they're functions of random variables. So that's why, people confuse the idea of the mean with the average. The average, at least in a statistical sense, the average is the average of these random variables. This thing, well, if I divide it by n, it would be the average. The average is a random variable. The mean is not a random variable. So they're two entirely different things. The average is an estimate of the mean, but they're not one and the same. Okay? So, so I'll let you go now, and then read the notes, because it'll make it much easier when you come to class, okay? All right, thanks a lot.